So when people hear the term, or when I bring up radiography, the term that most people are probably most familiar with is X-ray, right? Majority of you, if not all of you, at some point in your life have had some kind of an X-ray. Whether it's teeth at the dentist, right? Or you've had some kind of an injury where you've had to get X-ray done at a hospital or a clinic setting. You know, people are familiar with it from the perspective of medical care. But we can also use X-ray radiography and then another form called gamma radiation radiography to inspect the internal parts of a component or even an aircraft. We used to do X-ray radiography of the wing spars of our aircraft at the first airline I was at, because you could access areas without having they were areas of the wing spar that had to be checked for cracks that were not visible without doing some major panel and disassembly, which really could only be done at C-check efficiently, and it had to be done more often than C-check. So what is radiography? So we're going to take electromagnetic radiation. It's very short wavelength. We'll look at the spectrum here in a second. And as we pass radiation through an object, some areas it's going to pass through easier than others. Some areas are going to have more resistance to this electromagnetic radiation traveling through. And so what we can look at is, how does it compare? Those areas that, you know, what do you get different absorption in different areas? And so denser materials and materials that are certain materials are going to absorb more radiation, while less dense materials tend to absorb less radiation, and then also the thickness, the geometry of the part. So thicker materials are going to absorb more radiation than thinner materials, or thicker areas versus thinner areas. And so what that means is something like a crack or a flaw, you know, corrosion, for instance, causes thinning of a material. And so areas that are corroded, you'll get more electromagnetic radiation or X-ray or gamma ray transmission than areas that are not corroded. And areas that are cracked, those cracks are going to be a path where radiation can travel fairly easily compared to the non-cracked or non-flawed areas right next to them. So if we're looking at the spectrum, we've done different areas. We just got done talking about infrared. That's, you know, those are lower frequency and longer wavelength than visible light. And we've talked about using ultraviolet, higher frequency and shorter wavelength rays than visible light. And then we've talked about visible light because, of course, we did visual inspection and that kind of thing. So now we're looking at the very high frequency end of the spectrum. And so X-rays run from about, if you look at frequency, it's about 10 to the 16th hertz up to 10 to the 20th hertz, which is in the peta and terahertz range is the terms for them. Gamma rays start at about the 10 to the 18th, 10 to the 19th range, okay? So gamma rays are at the very high end of the radiographic spectrum. X-rays are a little bit wider range of radiographic spectrum, but that whole thing is, you know, essentially above ultraviolet, you're getting into the radiographic spectrum. And so those are very, very high frequency. They're very, very short wavelength. Okay? And that's what allows that to pass through. It actually can pass between atoms because the wavelengths are so small, they fit in the spaces, they can travel through the spaces between atoms and molecules. So there's a box with that outlined. Okay? So the advantages is we can find those very, very small, very, very fine flaws that are not going to necessarily be visible. We can detect internal flaws because we're passing energy through an object and looking at what comes out the other side. We can find things internally. We can see different variations. And then in the past, originally this was all done with X-ray film. We used film as our detector source. And that created a relatively permanent record. Nowadays, we use a electromagnetic detection source hooked up to a computer, basically a panel that can detect X-rays. and that sends a signal. Now we get a computer file out of it, an image file for our computer. And that's pretty much what the industry is today. Almost everywhere has gone away from film. Film is a big pain, right? Film has to be protected from light and other radiation sources. Film has to be developed. You have to have a special processing room. They call it a dark room. It's not light sensitive, it's X-ray sensitive and gamma ray sensitive, but you have to keep it, there is radiation in the atmosphere just around, so you got to be careful it's not exposed to too much atmospheric radiation or the film goes bad. So we've gone away from that. We've gone to electronic detection sources. In fact, I had an X-ray not too long ago when I had this knee stuff going on, and the detector panel they use is now wireless. So they had an X-ray source they kind of put here, and the nurse was able to, or the X-ray tech was able to just set basically a panel behind my leg, and it didn't have wires connected to it or anything. They could pretty much move it wherever they needed to. It was pretty cool. Disadvantages, however, as we've all probably are aware, radiation is hazardous. We have to protect us from it. That radiation, as it travels between the atoms and molecules, sometimes hits atoms and molecules, and hits cells in our body, and hits strands of DNA. And when it does that, it causes damage to them. And that damage can lead to, in humans, things like radiation sickness, short term, or long, like terminal term. If you get high enough radiation sickness, it'll kill you. Or long term can lead to things like cancer. And so we have to be aware of those risks and protect ourselves from them if we're working around these radiation sources. So because of that, we have significant handling and tracking procedures. We have to track how much exposure people have to the radiation. We have to track our sources. Gamma radiation so X-rays are done by X-ray producing devices. We'll show you that. Gamma ray comes from sources. They are materials that give off radiation. So you don't want to just lose your radioactive material and not be able to find it again, right? Or you don't want it to end up in the environment somewhere. And so we have to track that kind of thing. So in the United States, the Nuclear Regulatory Commission regulates both X-ray and gamma ray, and it's a very costly and time-consuming process. The university, Western Michigan University, has an entire department dedicated to working with the NRC because they do use, there are areas on campus, departments on campus that use both X-ray and gamma ray equipment, particularly in the medical area, right? We have a medical school. In the sciences where they're doing lab work, right? Lab animal testing and that kind of thing. So, it's not great in that regard. It is a pain. If you can do it another way, oftentimes it's preferred to do the inspection another way. And that's where a lot of these other techniques have gotten better and kind of replaced X-ray. But there are certain things you just can't do without using this. And then not suited to assemblies that are made from similar materials. You've gotten a medical X-ray, right? If you get one done at your doctor's office or at your dentist's office, your teeth and your jawbone look pretty similar, right? I mean, you can tell them apart, and they're trained and they know them apart, but that's just the thing. Those are both very dense. The rest of your tissue, muscle, skin, whatever, passes right through. That doesn't really show up on there. So you can tell those apart, but if you get two materials like teeth and bone that are similar, there's not a ton of contrast there. And the same thing occurs, like two alloys of steel aren't going to look much different under X-ray, because steel in general absorbs X-ray in the same manner. So you got to have differences, either material differences that have different X-ray and gamma ray absorption properties, or again, the different thicknesses, the geometry. So the energy, what we have is an X-ray or gamma ray starts out with a certain amount of energy, and we're going to pass it through an object. And so you can adjust how much energy you put into the object to begin with. And with an X-ray machine, something that does X-ray, oftentimes you can adjust the power output of it. You can also adjust how long that you're putting out the X-ray, the amount of time. With a gamma ray source, the power output, so to speak, is fixed. It's based on the nuclear fission taking place within that gamma ray source, the breakdown of unstable isotopes. But you can adjust how long you expose your test object to that radiation. And so what you have here is the same component with a low energy radiation. So you can think about it as a short and a long burst, or you can think about it as an X-ray turned down lower, turned up higher. When we get into exposure to humans, it's the same thing. The exposure is it's a factor of both time and intensity. Okay? So the low energy could be low time, or it could be low intensity, or it could be both. And the high energy radiation could be a longer time, or it could be a higher intensity, or it could be both, right? And so what you have here in this part, you can see the areas that absorb radiation. You know, this is the way these are viewed is based on how the film worked. The film started out white, or kind of a silvery color. And as it's exposed to radiation, it gets darker. Okay, so the areas that are thin, where it's easy for that radiation to pass, are going to be the darker areas. And the areas that are thicker or heavier or more radiation absorbing materials, greater degree of absorption, the film is not going to turn black. It's going to remain more of a white. And even with the modern electronic detectors, they still use this black-white scale as the most common for viewing things. Now, a lot of times we're getting into color scales now, color systems now too, to help differentiate even more. But at the end of the day, it's, again, like we talked about thermography, if the computer is looking at it, it's purely looking at the numbers. Right? If you've got an electric detector, it's looking at the strength of the field being absorbed at each sensor point. And then it can put colors, black, white, some shade of gray in between, or it can even go into using a color scale. But when it was film, it either turned dark black or white. So same object, higher or lower. But now you can see here with low energy, we can kind of examine the center area. It's hard to see anything on either end. With high energy, we're not now able to see the center area, but now we can do a little bit more inspection in. So you may image the part with X-ray or gamma ray. You may do it slightly different ways to be able to look at different areas, right? It doesn't mean this is overexposed. It just means it's overexposed in the center, but now we can see details on the ends. Over here, it's underexposed at the ends, but we can see details in the center where it's properly exposed. Okay. So that's where we're going to leave off. We'll pick this back up again on Tuesday.